This video is featuring Diamond Head Lake. So I am sitting next to a beautiful lake, very calmly, talking about combinations of functions. What you're going to want to take away from this video is being able to add, subtract, multiply, and divide two functions. So that's one method of combining. The other way of combining is what we call compositions of functions. This will be probably the newer of the two. There's a certain notation that goes with it to understand, and then also how to do it. Alright, so the definition of sum, difference, product, quotient, I know you already know that, but it's how it's notated that you truly have to understand. So how your book prefers to notate that you have to add something is they're going to write f plus g, just like this, of x. The more easily understood look, I would say, is if f of x plus g of x was the way they notated it. So these on the right hand side are probably the more easily understood of exactly what you need to do. And so all that is it's saying if you knew your f function, add it to your g function. That's what both of these are saying. I just think the right hand is a little bit more easy to understand. So when you are going to be combining these functions using operations, it's going to look something like this. Let's do part A first. When you look at part A, again, all that's saying is take your f of x function plus your g of x function. Okay, so all that is going to do then is saying we'll take whatever f of x is equal to and add it to whatever g of x is equal to. So slap those in there. Technically what you do need is groupings, but because this is addition, remember addition is associative, so groupings don't really matter. So now you're just going to combine these. Order of operations when you change everything to addition doesn't matter either. So now we're just taking 2x plus negative x, that's going to be x. And then we have negative 5 plus 2, so minus 3 would be what you would get if you combined these like terms. B, again, all that's asking for is f of x minus g of x. So what we're really doing is we're just going to be taking, well, what is f of x? Again, that's going to be defined here, minus g of x. This is where the groupings do matter, because subtraction is not associative like addition is. Order does matter. So we're subtracting this whole g of x, this 2 minus x, so you have to distribute that subtraction to everything. So it would be 2x minus 5, and then we would have minus 2, and then minus negative x, so plus x. And when you simplify and combine these like terms, what we're going to get is 3x, and then we have negative 5 minus 2, so minus 7. Part C, this you might also see just fg, so this is going to be f times g, so we're going to have 2x minus 5 times times 2x, 2 minus x. So these do have to be in groupings. You would have to go ahead and FOIL these for your final answer. And D, you're just going to be taking them and dividing f of x divided by g of x. So it would look something like this. And there are no common factors on top and bottom. Don't take these two and divide them because they're families. So this would just be done. This you would have to FOIL, but I'm not going to do that. I think we all know how to FOIL. Alright, the other type of combination that we're going to look at is a composition of functions. The definition of a composition is down below. And what that is doing is it's just saying you're going to take a function and put it into another function. Or you're going to take an input, put it through one type of operation, and then you're going to take whatever you get there and put it through another type of operation. So the idea is, I did an analogy here, if you take fiber, you put it through a function that makes cloth, then you're going to take that cloth and you're going to put it through another function that would make clothes. So that's my analogy. Maybe that might help you understand it. But here's the notation that's going to be presented whenever they want a composition, and it's just this open dot. It looks like multiplication, except for it's a bigger dot with a hollow inside. So this is saying take f of g of x. So it's in the exact order for which it appears. So f, I like, again, the right-hand side. It would be f of g of x, but ACT's books are going to use that hollow dot. This makes more sense, and I'll be rewriting all of these compositions into this format so that you can kind of see how the plugin goes. This one down here is going to be g of f of x. That's what it would be read as, or the composition of the g of f of x functions. Alright, so how these exactly work. They give us two functions, f and g, and they define them as you see up here. So if you wanted to find f of g of x, I'm going to rewrite it like this. Okay, so that's what this is asking us for. Fog, f of g of x. So here's where you're going to be saying, alright, you're going to take g of x and input it into your f function. So what exactly is g of x? Well, that's where you would go up and say, alright, it's defined as taking some sort of input and subtracting 1 from it. That's what g of x is. So I'm going to write that as taking an input and subtracting 1 from it. That's what g of x is defined as. Then now, when you look at this, it just becomes like all those other function problems that we were doing. You want to take this as your input and plug it into whatever the f function was. So you're going to see here that f is defined as taking an input and squaring it. So here is your input, you're going to square it. X minus 1 squared. And that one's done. You could FOIL that one out if you wanted to, but otherwise that one's done. So now we also have to find GOF, or in other words, g of f of x. That's what this one is down here, so I'll number this 2. This is 2. Alright, so now we want to take the f function and plug it into the g function, is what that's saying. So we're going to have to, let's look at first what is our f function. Well, it's defined as taking an input and squaring it, so there's what f of x is equal to. You can see how these are exactly the same. All I did was I rewrote f of x as what it was equal to, x squared. So now it's saying look at your g function, and wherever your inputs are, you're going to input x squared. So again, g is up here, and here's my input. But what I want to do is I want to input x squared in for that x. So it's going to become x squared minus 1. Okay. So there was my input. Here is my input that I put in for that g function. Alright, third one is FOF, or in other words, f of x. So you're combining the very same function this time. So now we're going to take f of x squared. Okay, and then we're going to take that x squared as our new input and plug it in to the f function again. So here is our input. We're taking x squared and we're plugging it in there, so x squared, and we're squaring it as the f function defines. And so this one, if you ever have an exponent to an exponent, that's when you multiply those exponents. We have x to the 4th. Alright, so the domain, again, we are focusing on domains. That's something that we just need to start looking at and considering more often now when we're studying functions. We need to figure out the domain of composition functions. What you're going to be looking for is the intersection, or the intersections of the two sets. So all you're going to be doing, another way of writing this, is that you're going to be determining the domain for both of your functions, domain sets for both functions, and then you're going to see where they intersect on the number line. Alright, so just kind of a sample of what that is if you had this set right here, it would be the same thing as x is less than 4, so all values less than 4. 4 is going to be the greatest value, and I'm not including it. And then anything below it, so negative infinity to 4 is what we're saying. So you can see how that's indicated on this number line that I've drawn below. Okay, so it's all those values. And then if you had x is greater than or equal to 1, if we were to use our interval notation, 1 is the smallest value that we have, and we would go way up until forever, so infinity. Always the rounded brackets around infinity. We do want to include 1, so we use the square brackets. That's this set right here. And what you can see is wherever there's overlap, that's what we call an intersection of two sets. So our overall domain, had this been the domain of one function, this the domain of another, and we took the composition of the two, the intersection would be the overall domain of the composition function. So to actually do this, let's look at f of g of x and g of f of x if we were to have these two functions defined here. So we're going to first, let's just do the composition. F of g of x, that's this right here. I'm going to evaluate that. So again, I'm going to just look at what is g of x first, that inner function. Okay, and then I'm going to input it into my f function. So here's where we're inputting, instead of having an x there, this time we're going to have an x squared there because that's what this is saying. Input that in. X squared plus 4. And again, this is one of those things that you cannot just take piece by piece because this is a grouping, so you would have to do all of this before you square rooted it. So this is as simplified as it can get. So this right here is f of g of x, done. Let's look at g of f of x. Alright, so g of, what was f of x? Well, that's that square root, x plus 4. And then we need to, extra parentheses, sorry. So then we're going to take that and we're going to input it into the g function, which says take your inputs and square it. So we would take this input and we would square it. So do note this one does simplify, alright, to be just x plus 4. Now this is deceiving because you would look at this and say the domain is all real numbers, but we have to take into account that we had to go through inputting into this function before we ever would be able to input it into this function. So we have to look at both of the domains in order to determine the composition's domain. So let's just go ahead and say this is the one, f of x domain, f of x's domain is where we're going to have an issue. So remember, watch out for those radicals. If we ever have a radical that's an even root, we need to have values underneath it that are greater than or equal to 0. So when we solve for this, x has to be greater than or equal to negative 4. So I'm going to write that in our proper notation that we're getting used to. I'm going to include negative 4. That's our smallest value because then we want all values greater than it to infinity. So on the number line, that would look something like this. We have negative 5, negative 4, negative 3. I'm going to include negative 4. Whoops, I'll use my square brackets. And then I'll go forward because I want all values greater than or equal to it. So then I have to look at g of x's function. Now g of x's function is just a polynomial. There's nothing that would cause a problem with me inputting into it. So this is actually from negative infinity to infinity. So I'm going to go ahead and just shade everything from here to there. So now the overlap occurs right here from negative 4 all the way to infinity, and it does include negative 4. So this right here is our composition's domains, okay, for both of those. Alright, so there you have it. That is how you find the domain of the composition functions. Alright, there's your homework. Good luck.